Welcome back to our routing protocol discussion. And in this part, I'm going to be talking about routing on the internet and specifically BGP protocol. The global structure of the internet is actually quite complex. In previous parts, we talked about RIP protocol, Ospf protocol, and in those cases, the assumptions are a bit quite simple. You have some connection of routers, you have links, and you just want to calculate the shortest path to each destination. In RIP, there's also limitation of number of hops. Technically, some limitation exists in Ospf, but that's not the biggest problem. The biggest problem in Ospf is the fact that every single router have to know the whole topology. And in principle, it's not a big deal, but it's a bit of a commercial secret, and they don't really want to disclose how many routers they have, how many links, what kind of connectivity inside the network. So it's running Ospf on a global scale, it's actually not an option. And as a result, for kind of discussions, understanding of desire of different ISPs, what they have come up with is a concept of autonomous system. So autonomous system is basically some form of a network. And inside this network, you can run whatever you want. You can run Ospf protocol, you can run RIP protocol, or you can just configure everything manually. It doesn't really matter. From the perspective of the outside world, like from the perspective of global routing, this autonomous system, or AS for short, is considered as a single entity. And depending on the position of individual AS, you can consider them as stub AS, basically some form of customer, like a FIU network or kind of a big consumer network, and a transit AS. And a transit AS is basically the ISPs of like that the stub ASs are using, like Comcast, AT&T can be considered as a transit AS. But there are also class of ESs, class of transit ESs that are providers of providers, like providers of the providers of the providers. So the ones that don't really deal directly with customers, but rather with the ISPs themselves. And to give you kind of a high-level picture of how this internet is actually structured, so you can see there's basically several tiers. If you go from the bottom, so basically we have some tier representing the customers. So this is really not individual customers usually, but rather big customers like FIU, big companies that are connected to AT&T and Comcast, like one provider, multiple providers. It doesn't really matter from this perspective. Then we have a tier 3 networks. So basically these are our ISPs. AT&T technically have multiple positions in this environment, but you can consider them. Comcast also have multiple positions, but there are smaller ISPs, I don't know which ones you're using, that can be considered as tier 3 ISPs. Tier 3 ISPs technically kind of may not be able to communicate with everybody on the internet. So they have their own customers, they can send them traffic directly. They may have some interconnectivity between different ISPs internally, so-called peer-to-peer connections. But they still have very limited knowledge of the internet. And to actually get the all packets forwarded, they have to connect to their own ISPs, again, one or multiple ISPs that you can consider transit ones. Also transit ISPs, but they still kind of have a bigger coverage that can cover the whole country, half of the country, city, or like something bigger than the tier 3, but not yet the global ISPs. And then finally, there's a special class of tier 1 ISPs, and there's quite a limited number of those tier 1 ISPs that basically know how to forward everything. They have presence in multiple continents, they have presence in basically all countries, or at least the majority of the countries, and they know how to forward a single packet. And all these tier 1 networks are connected to each other, and if some tier 1 ISPs doesn't know how to forward, it will send it to the peer. But tier 1 ISPs don't have their own provider. So this is the provider of the provider, so the main guy in the network. This is a very structured picture of the internet, like where I specifically separated different tiers at different levels. And usually it's kind of when you see the picture of different ISPs, it's not that clear who is who. And what you can do is actually try to understand the money flow, like who is provider of whom and who is paying to whom. So basically, if you're a consumer or a customer, you will pay money to the provider. And if you're a provider and you have your own provider, then you will pay money to that provider. And if you have like a peer-to-peer agreement, then potentially money would flow both ways. So if I, for example, show this link, so there's some consumer, some ISP, the money would flow this direction. If I'm transit and connected to tier 2, the money would flow that direction. And finally, if I'm as a tier 2 ISP is connected to tier 1, the money would flow that direction. And you can draw the pictures in a similar way in different places, like just with these arrows. So these arrows in some form represent the relationship between ESs, and those relationships can be consumer-provider, like consumer-provider. You can reverse that would be provider-consumer, but it's kind of the same thing. And it can be peer-to-peer. So for example, in this case, you can set up some form of a peer-to-peer connection that money flows potentially in both directions, or there is no money flow in the first place. Because it's peer-to-peer, everybody is friendly. To give you yet another representation of different ESs is a graph that was compiled in 2015 that's trying to show you how many different ESs and how they're actually interconnected. What you can see on this picture is internal structure. So what you can see on both IPv4 and IPv6 pictures, that there is this central core of very, very highly interconnected networks, which represent tier 1. After that, there is like area of less connected networks. Like in both cases, it's slightly different representation, but still we have them. It would be tier 2, and smaller version of smaller, like a bluish color representing even less connected networks, that is tier 3 networks. And finally, there's a consumers and even tiny networks like a home networks connected to the internet. At this point, I hope you got the picture that there's ESs, they're connected in some way, but now get back a little bit to kind of internals of individual ESs. So ESs is a simply logical representation of one network from in the global perspective. But remember that one network has still its own routers, like it still has its own routing tables and so forth. So technically, there's a technical term of intra-ES and inter-ES routing. So one is representing routing inside ES, and the other representing routing outside ES. Like basically, from the perspective of intra, you don't care what happens in outside world, and from the perspective of inter, you only need to know basically how to reach the different destination outside world, and maybe have a knowledge of how to reach routers inside the network. So this is basically what highlights inside the network. The routing tables will have some information coming from the inter-domain routing and some information coming from intra-domain routing. And I gave you examples of intra-domain routing is Ospf and RIP that we discussed before. And the inter-domain routing, this is the one that the focus of this part is BGP, or Border Gateway Protocol. BGP Routing Protocol operates in terms of autonomous systems. So basically, it considers individual autonomous system as one thing. And like if it decided that the packet needs to be forwarded through that specific ES, it needs to be forwarded by some whatever means to that destination. It still in some way needs to figure out IP addresses, how to forward, but it's a slightly different concern that is not part of the BGP calculation. And essentially, BGP implements so-called the path vector protocol. It is in some form similar to distance vector protocol, but instead of just having a distance to each destination, so remember there was a vector to each destination, I have one number representing a cost to reach that destination. In a BGP protocol, instead of this number, we have the whole path. So for example, if we have destination A, B, and C, we have some form of ES1, ES2, ES3, ES4. So basically, literally explaining the whole path, and it's something similar to the destination. And as a metric, BGP uses the length of this ES path. So kind of the shorter ES path, then the more preferred this destination. So the less number of hops in terms of ES, the preferred way of reaching that destination. So it's kind of logical, but remember that this is not exactly a number of hops, because hops are based on the routers, but these are ES hops. And as soon as you reach this specific ES, you potentially need to go inside of several routers inside the ES, and then reach the exit point of the ES, and then go to another one. You can go a few hops inside the ES, and so forth and so on. But from the perspective of BGP protocol, this is all that BGP protocol is looking at, the ES path. And when you advertise some information, you actually advertise in the prefix, and you associate this prefix with specific ES path. And if A wants to communicate with B, it will basically tell some information to B if it wants to kind of route packets on its behalf. And that network B will know that now it can reach certain prefixes through that network. And if you have multiple connectivity, you will calculate which neighbor, which ES you prefer to use for forwarding specific packets. That's basically it. This figure makes several highlights of BGP protocol, just showing a little bit of internals of individual ESs, because ES still contains routers, and routers actually connected with links. So, but just to give you a small perspective. Let's say assume we have this 12.3.6/24 as announced inside ES3. So that's kind of ES3 knows that this is the prefix belongs to this ISP. However, ES as abstract cannot do the announcement. What needs to be done is the BGP routers on edges needs to do this announcement. So basically in BGP protocol, we have this 3B and 3A will act as actual gateway nodes that will do some form of announcements. The announcements, unlike, again, Ospf and RIP protocols, are not done to direct neighbors. So direct neighbors in terms of adjacent links. What happens in BGP protocol, you actually establish so-called session to the other side, other neighboring ES BGP router. That doesn't have to be at the actual border. Usually it is, but it doesn't have to be at the actual border. And there is a basically TCP connection between these two. So this is just to highlight there is this TCP notions, because that's different from all other protocols. Now we rely on TCP to give us reliability to the transport. If we send some message and this TCP connection is still alive, then we know that the other side still have that message. If TCP connection broke, then we know that we potentially need to resend some of the information. But in any case, so this is what happens. So for example, node 3A acting as a egress BGP router from in the system make the announcement. And in this announcement, it simply specify that 12.3.6.0/24 is reachable with the ES3. So that's information being sent out as part of this exchange. This information got propagated inside the network, and I will highlight how exactly it happens. And then BGP router in ES1 made similar announcement between ES1 and ESB, but in slightly different form, because now it's remembering the whole path. So what it's saying is 12.3.6.0/24. It's saying that it's reachable through ES1 and then ES3. And finally, again, there is some propagation inside the network, and there is more announcement between ES2 and some other networks, which will get a form of ES2, ES1, ES3. So I think it's clear where I'm going. So every time I'm doing a re-advertisement, I'm appending myself as part of this re-advertisement. And as I highlighted, because of the length of the ES path determines the shortness, like the preferred path, kind of that effectively, if everybody get the information and calculate the routing and see the path, they can simply pick the shortest path. And then there's the small adjustment. If you want to make the path less preferred. So if you want to advertise that you have the path, but you want to make sure that, oh, but I don't really want you to send traffic to me, you can prepend yourself multiple times. So for example, you can advertise this way, but you can also advertise ES3, ES3, ES3. Technically, it doesn't change anything. Like it's still ES2, ES1, ES3. And kind of from the perspective of others. But this path will be less preferred to be picked by others because it's longer. That's basically the only complication here. As I was highlighting before, inside the network, there is some magic happening with this BGP, because you receive announcement on one site in one BGP router, but technically you may need to get the announcement out on other BGP routers that's connected to a completely different network, in maybe even in different city if your network is big. And for that specific reason, BGP actually has two parts. So it has a eBGP, so that's the one that's external, making the sessions with the external AS BGP routers and exchanging the information about available routes, AS numbers, and all the magic that we just discussed. But then there is a iBGP, also called internal BGP. And the whole purpose of this internal BGP protocol is to exchange information that you receive from the eBGP and kind of propagate it to all iBGP nodes, all other eBGPs. So basically, like each BGP router have the both parts, like there's eBGP and iBGP, and eBGP is talking to the outside, and iBGP somehow synchronizes the information inside the network. And of course, there's still internal routing, like there's only intra-AS routing protocol that is actually defining how packets are flowing inside the network. Because these two guys, like 1B and 1C, that are acting as a BGP, both I and E BGP routers, they still need to send information somehow between each other, and how it's done, whether it's done directly, whether it's done indirectly, is defined by intra-AS routing protocol, such as Ospf or RIP protocol. That's basically it for discussion of BGP. In addition to ES path that already briefly discussed, BGP protocol also has next hop information and local preference. And the next hop is basically IP address of the actual router that you can send packets to. So for example, as eBGP, you would do advertisement of I can reach that prefix and this is AS path, but you also need to specify what is the actual gateway router of this network. Like if you have a connection between ES1, ES2, there's some IP address of the router here, some IP address of the router here. And if ES2 received this update from ES1, so ES1 better to say what is the IP address of that server. So very, very, very simple here. And the local preference is a slightly different mechanism of how you want to adjust, or what is the mechanism to adjust the route to be picked by somebody else. So for example, one of the mechanisms that I discussed, you can prepend yourself multiple times. It works, but it's a little bit not nice from the BGP perspective. And for the local preference is actually just a number that you can attach to the route saying, oh, if I'm advertising these two routes, you better prefer this one because this is more like backup, it's slower, or as some other reasons I have to kind of not prefer that route versus this route. So basically that's it for the BGP local preference. Moving to a little bit more complicated topic, Bgp routing policy. And what it actually means is when you have information about that you can route packets through these certain paths, it doesn't mean that you have to tell others that you can do that. So for example, as a customer, it kind of would be stupid that you tell your provider or your second provider that you can reach some certain destination. So for example, if X is some specific customer, it can reach all prefixes through B, it can reach all prefixes through C if it's sending packets. But it would be kind of stupid to tell that that X is telling B as its own ISP that it can reach all the network through C. Because now the B as your ISP can potentially use your network and then your connection to your other ISP to forward packets. So basically, B can save a lot of money if it's actually doing that. Like if all customers, like dual home customers, can do that, like will do that, then B will be happy because it wouldn't actually need to pay any money to its own provider. So this was basically the highlight and the reason I was telling you before to follow the money. So in this picture, money will be flowing this way, and potentially some kind of this way. So this is the basics of the BGP policy. You only advertise prefixes to your provider if you own those prefixes. So for example, X, it actually need to advertise its own prefix to both B and C. And in addition to that, if X has its own customers, it's also need to advertise those prefixes. So X needs to tell, like if there's some network in here and the money flows in that direction, then X still need to tell both B and C that it can forward those packets. Otherwise, neither of those two guys will be able to know how to do this. There's this special peer-to-peer connection is a little bit special, and it's been considered as you still tell the other node, the other side, that you can forward from C's perspective is telling B information about X and Y, and from B's perspective, it's actually only telling information to C about X, because that's what's been advertised in this specific case. And that's basically the policy. It actually have a slightly different name. It's actually called No Valley Policy, and what it simply means is if you build a structure that I was showing you, like there's a consumers, tier 1, tier 2, tier 3, tier 2, and then tier 1. You like when you forward the packet, you always have to go up, and you can only go up once, and then you have to go down in some way. I hope this logic is simple, but as I said, the picture is not always that simple, because you don't really have a relationship like nicely structured. And if I draw a completely different picture, so for example, if I completely randomly pick ISPs and put them on a graph and do some form of a connection between them, and then I will try to ask the question, what is the no valley policy? Whether this node can send packet to that node over that specific path. In order to complete this picture, because it's not fully structured, I need to specify the relationship between them. And the relationship between them is a consumer-provider, peer-to-peer, or not to peer-to-peer. And I can do that with simply defining the arrows of money flow. So what I'll do, I'll define it this way, I'll define that way. Let's say this will be peer-to-peer. I'm not sure how to define it. And this will be the provider. So this will be one, let's say A, B, C, D, and E. A, B, C, D, E. So that's basically the network. And then if I ask a very simple question, I need to do something here. So for example, this will be also money flow this direction. Can I send a packet from A to E, like over this path? That's a good question. To answer this specific question, that you need to kind of remember what exactly no valley policy means. And it has a few complications, basically. So one thing is you always have to go to the provider. So you can always go to the provider, but you cannot go to the provider of the customer. So like as soon as you reach some provider that they gave you packet to the customer, you cannot go back again. So if I kind of do some renaming here, if I define a consumer-provider relationship, and then consumer-provider, what you can do is you can pick consumer-provider, you can keep a consumer-provider. At some point, potentially, you will go to provider-consumer and some other provider-consumer. So this is the possible path. What you cannot do is consumer-provider, consumer-provider, provider-consumer, and a consumer-provider. So this one, like if in some form in existence, you cannot do that, because it will be going up, going down, and then so this is up, and this is so this one is down, and this is up. So you cannot have up, down, and up. So this creates basically some form of a valley. So that's no valley policy. In this specific picture, we actually have a slightly different. We also have a notion of peer-to-peer, and they have yet another complication. So let me just draw the picture. So what we have is a consumer-provider, peer-to-peer, and then again, consumer-provider. And for the fun of it, I'll try to do it the opposite way. So we're going to have a provider-consumer, peer-to-peer, and then provider-consumer. So this is for the path from A to E, like when I'm sending packets from A to E, and this is for the path from E to A, from E to A. Okay, so now looking at this picture. So now we have up, we have a basically straight line, and we have up. So technically, this one violates the no-valley policy, because even though it's not really a valley, you have a go to some point, you create a plateau, and you go up again. This is the problematic part. You cannot go to the plateau this way. However, on the way back, what we see, it's actually going down. We have a plateau, and we're going down. So this one is actually allowed, because we kind of go into the customer. That guy knows that it can reach its somebody else using the peer-to-peer network, and it will go down. This environment may not be too common because you're probably not going to advertise those prefixes, but this is not violating no-valley policy. So the violation is if you go up, then down and up. So this is kind of, the valley is not allowed. Or if you do up, plateau, up. So this is plateau on the way up is not allowed, but plateau on the way down is allowed. So this is basically trying to highlight that try to follow the money with a few specific extensions for the peer-to-peer, where you can. So this format is not allowed if you go up, but if you go down, this is allowed. Or again, if I'm looking at the going up, so this is allowed. This is okay. If I go up, a little bit down, and go up, so this one is not allowed. So kind of not possible. So this, all of it is basically this no-valley policy. Again, it maybe looks a little bit more complicated than it actually is, but just try to remember this no-valleyness or no plateauing on the way up. Okay, so I'll try to stop here about the BGP. It's already quite complicated. As I highlighted, BGP protocol is a path vector protocol. It's some kind of variation of the distance vector, but not exactly. Because it's a variation of distance vector protocol, you actually don't have to disclose the whole topology of the global internet. You only need to disclose basically very, very limited information. And because it's actually on the granularity of ESs, in BGP, you don't actually tell anything about your internal network. But what you don't have to tell others is all your connectivity to others. You only basically tell what you want to tell, and that it does not violate the no-valley policy. But you don't have to even tell all complete information that does not violate the policy. ES path, this is the kind of component of the path vector protocol, is being used as a metric, like the size of the ES path. In addition to that, you can use local preferences, and there are a few other attributes that BGP has kind of to adjust the selection of specific routes. And from the protocol perspective, BGP uses TCP protocol, and as such, it's more like considered as a hard state protocol, where you create the connection, and as soon as you create the connection, you do some initial exchanges to get the database from the other side, to give to the other side all the information that you have. And after that, you assume the other guy knows everything that you told him. As soon as you create some kind of an update, you immediately tell the other guy, and assuming that everything knows. And there's no other type of public updates. Note that I didn't talk anything about the timing, because everything in BGP protocol, as soon as you discover information, you tell others about the information. There are special cases of timers, technically, but you can consider at this moment that everything is fine. Okay, so that's it. What I want to talk about global routing, and that would be end of our routing part. I know it was extensive. We had 3 parts for the routing protocols. We had 2 parts for the routing algorithms, but this is a really, really fundamental part of the routing system for the networking module. So I hope you got a lot of information. I hope you remembered some of the information, and I will try to check that in homeworks and the exam. But remember, these are very, very fundamental parts. If you have questions, I'm happy to answer them over email or any other source. But hope it was interesting, and see you next module.